Hello, everyone. Welcome to CPE 517, Digital and Computer System Architecture. This is lecture 4, part 1, virtual memory. First, some logistics. These slides, some of them are from Digitech, Rodriguez. All the credits goes to original authors. Other errors are mine. Reordering and modification might be made due to requirements. So the outline of today's lecture will be virtual memory organization and virtual memory caching. Okay. So I bet a lot of you guys know what is virtual memory, right? So virtual memory is the OS abstraction that gives the programmer the illusion of an address space that might be larger than the physical address space. Virtual memory can be implemented using either paging or segmentation, but the paging is mostly used. The combination is also used, but the segmentation scheme is typically very simple. Virtual memory is motivated by both convenience. The programmer does not have to deal with the fact that individual machines have very different amount of physical memory, and fragmentation in multi-programming environment. Okay. So to enable virtual memory, you need a physical unit that is called memory management unit. The duty of memory management unit, or MMU, is that it handles the DRAM refresh, like we discussed in last lecture. Every time when we read the DRAM cell, it discharges the power, or it basically just leak the power. So that's why we have to refresh it to maintain the correctness, the correct voltage of every memory cell. It takes care of the memory sharing among multiprocessors. It translates the logical memory address or virtual address from processor to physical memory address of DRAM. Modern CPUs often have the MMU built in. So you have to keep in mind the MMU is featured in CPU, but then for DRAM. Okay, it's in CPU chip, and then do that for DRAM. Single purpose processors can be used for MMU as well, like one processor that is the single purpose, that's just to do logical memory translation and handling the DRAM refreshing, right? So here's the thing we say, like a pyramid of memory hierarchy. We have small and fast register, slightly smaller, slightly larger, and slightly slower cache, and very large, very slow memory. So what if we want to support a program that requires more memory than physically can provide it? For example, this is 4 GB and our program requires 8 GB, right? We introduce virtual memory. Virtual memory gives you the illusion that we have infinite amount of memory by swapping the unused memory out and always keep the used memory in. Okay. Virtual memory is a separation of logical memory from physical memory. Only a part of the program needs to be in memory for execution, while other that's not used memory logical addresses can be swapped out of the memory. And also the sort of the illusion of the virtual address or logical address can be significantly larger than the physical address. This also allows the space of different processes to be shared. It allows more efficient process creation as well, because we don't have to really claim so many physical memories before we create the process. Actually, we can just do it on the run, right? Virtual memory can be implemented about demand cache or demand segmentation. Let's discuss them later. And right now, we want to tell you like virtual addressing and what's the benefits of virtual addressing, right? The concept of a virtual or logical address that is bounded to a separate physical address space is central to memory management. Virtual address is generated by CPU. Physical address is seen by memory, and then CPU maintains the translation from the virtual address to physical address. Virtual and physical addresses are the same in compile time and load time. The virtual and physical addresses are different during execution time and address binding schemes. The advantage of virtual address are typically threefold. First, program can be given consistent view of memory, even though physical address memory is scrambled. Like you see a continuous range of 4 GB, but actually this 4 GB might be scrambled into different places. Like I give you this 10 megabytes here and 100 megabytes there, and maybe 1 GB here. They are like at different physical locations, but you see the illusion that this entire 4 GB is continuous. So we see this is a consistent view of memory, even the physical memory is scrambled. Only the most important part of program must be physical memory. That's what we say by when you claim 8 GB, but actually you only deal with like 100 megabytes, then we only give you 100 megabytes. The other spaces are swamped out of the memory. So that's why in the operating system, you always have a swamp space out there. It also supports continuous structures like stacks, only use as much physical memory as necessary, and you can grow this later on. Like when, that's why you have dynamic structure, right? So you always can grow on demand, and also even you claim large, you don't have to really claim, give all the physical memory at first glance. The second one is very, very important. That is protection. It protects different threads from each other. Different pages can be given special behavior. Like read only, it's invisible to user programmers, or kernel space data, so that the user program can just simply cannot touch it, right? Very important for protection from malicious programs. I think right now, if you guys check online, there's so many cyber attack problems. Well, virtual memory is one of the schemes try to prevent those cyber attacks from accessing the data, because if the data is in the kernel space, no matter how like what leakage you did have, it gives a protection for the data from the cyber attackers, because they simply don't have the privilege to access this kernel protected memory space. Well, in Microsoft and a lot of other previous operating systems, they don't really have such rigorous protections, but right now I think they do. The third one is sharing. Imagine this case. Like when, I don't know whether you guys have this kind of experience before. Do you guys use Amazon AWS? Like or Microsoft Azure, or Google Cloud, or whatever. There's so many cloud providers. What they do is they provide you a lot of softwares. For instance, if I want to use MATLAB, right? Well, or Photoshop, right? And I remember for Photoshop, every year you have to pay around $1,000 to use it. But what I really need to use is probably a couple of hours. And you guys are also similar. Like you also want to use Photoshop, but you really don't want to pay $1,000 and own that for an entire 1 year. 365 days or 6 days. So what we do is we go to some cloud provider like AWS, and then we run a machine that has the Photoshop. And then what we do is we're gonna create a user in AWS and then load the Photoshop here and try to use it, right? Well, there's another user. This is user one. They also want to use Photoshop because this is a service like a provider. Then definitely there's a lot of people want to use this same the same application. So in that sense, maybe the second user also want to use Photoshop. So when we are residing on the same physical machine, there are chances we can use KSM, kernel sim page memory, to just create one single copy of Photoshop and then let both user one and user two use it. It's the same as Microsoft, right? And when we go to Windows operating system and then multiple users, both of them are using, one of them are using Microsoft, then we can only create a single shared content for both processors. Well, another very popular way of doing this is inter-process IPC, inter-process communication. If you guys learned the difference of process and a thread, okay? A process versus a thread. So you see, you know that process has their own memory space, right? Stack, heap, etc. And then how do we allow processes to communicate? We can use this kind of shared memory. Like we use this, basically what we do is we let both processes have different virtual address, right? But actually, when we translate that into physical address, they're actually the same physical address. So I'm holding this physical address, you are holding another physical address. For instance, in Stevens, the street in front of Burchard is the same as the street in front of Barbie Center, right? So in my mind, I'm living in Burchard building, so I assume, okay, the street in front of Burchard is the street I'm looking for to talk to you. Well, for the other people who live in Babio, then they feel, okay, the street in front of Babio is a street I want to talk to Hang. And then actually it's the same physical address, but it's just virtually or logically we treat it as different name. Okay. All right, I think that's it for part one.